Let's talk about displaying and summarizing data. Now, a big thing we're going to start with here is categorical data. Categorical data puts things into categories. It's also known as qualitative data. So with this, we have different ways of displaying something. I want you to think of a moment here and think of a categorical question. What is something that would lead to categorical data? Which one did you think of? So now we would think of how do we display that? Let's say you asked, what pet do you own? Well, what pet do you own could be displayed as a frequency or relative frequency table. That looks like, and we'll draw a little picture over here on the side. We're going to have a table right here with maybe dog or cat. We'll only include that for brevity's sake, dog or cat. And frequency would have the amount of people, where relative frequency would have the percent. That would be 66%, 33%. A bar chart for this same data we collected right here is going to show the amount of people in each group, which would be 8 and 4. So we could put a bar here for 8 and a bar here for 4. A pie chart is going to show the pie, and we'd see a slice of the pie where it's a 4 in this slice, 8 in that slice. A ring chart looks like a pie chart, just with the center cut out right there. So ring charts, not a big fan of them. They're kind of boring, just pie chart with the center cut out. And a Pareto plot or Pareto chart is going to be a bar chart that is put in order. So interestingly, the bar chart I drew is actually a correctly computed Pareto chart because the bars have been put in order. Not all bar charts are Pareto charts, so we'll do a little sub-indent right here to help us remember that a Pareto chart is going to be a bar chart put into order right there. So I consider Paretos to be subsets of bar charts where a bar chart has been put in order. It's like ring charts are a subset of pie charts, a pie chart with the center chopped out. So the first thing is once again a frequency table. You might say, Brian, wait, those are numbers. You said we're dealing with categorical data. If you remember the first lecture, we always ask ourselves, how do we phrase the question on how we collected data? So when we collected this data right here, we were asking a what question. We said, what class are you in? And think about how the person responded now. They said first class. Then we made a tally right there. We said this person's in first class. And now we have a count of the individuals in each category. So notice the answers to the questions are categories. And then the amount of people in each question is a number, but the data and the way we asked it was categorical. What class are you in on the Titanic? I'm in second class. Once again, nothing about the response is quantitative. We can summarize it. This is a summary of a categorical variable right here in a display called a frequency table. We can turn it into a relative frequency table. When you think relative, because we can do a relative bar chart too, relative just means we're turning it into percent. So once again, when you see a relative bar chart, that's not going to be a frequency bar chart. Frequency is going to show you the frequency of how often things occur. And relative means relative to a percent. So we can turn things to percentages to make it easier to understand which is the largest group. Clearly, the largest group is 40%, 40.35% were in crew. So they are larger than the other groups. A bar chart is going to look like bars right here. And do remember, this is not a histogram. A lot of people later on, when we get to that topic, will think of this as a histogram. But it's a frequency bar chart because we have over here the counts of observations or the frequency, and it's bars. A good way to know that's a bar chart, especially if you see words on the bottom right there, it will be a bar chart. So that'll be a good way to know it's a bar chart and not the other topic, which we'll talk about here in just a little bit. A pie chart. This is a frequency pie chart. Why is it a frequency pie chart? Because it shows the counts of the observations, the frequency of them. It's a pie chart. And to turn into a ring chart, just take out the center. Still a frequency pie chart right here, frequency ring chart. It's kind of a pie chart too. Pie, but somebody ate the center out of it. So with this right here, it is a frequency ring chart or donut chart. Not a big fan of these, but you might see them. All of this can be done inside of JMP right here with the analyze distribution, analyze fit y by x for bivariate data. Now I want to mention that important term you just heard me said, bivariate. We should also mention univariate. What in the world does univariate mean? Well, breaking down the word, we see uni and then variate. That means one variable is being displayed right here. Univariate is one variable being displayed. If we ask somebody, what animal do you own? We're asking one question. That is displayed in a univariate display. If we say, what animal do you own? And do you live on or off campus? And then display both variables at the same time, that would be in a bivariate display, and we'd have different displays to do that. So these are all univariate displays of categorical data. The displays we have will differ based on what kind of data we're analyzing and how many variables there are. Let's show one quick graphic right here and let you take a note on this. The important thing to know right here is which quadrant are we in? Well, the top quadrant is when you have one variable. You can see right there we have quantitative or categorical. The quadrants in the middle here, which I'm blocking part of, are for bivariate displays when you have an x and a y variable. We're only analyzing a y variable right now, so we are in the categorical with no x variable. So notice we have bar charts and pie charts. You can make a bar chart of your favorite pies and a pie chart of your favorite bars. We have pareto charts, which are bar charts put in order. We have frequency tables, relative frequency tables, and ring charts, which no one likes. Sorry, ring charts. Over here, we have quantitative data, which has different displays. So at this point, I highly suggest taking out your notebook and writing down all of these. As we go through the chapters, try to remember which quadrant we're in. Are we doing two quantitative variables? Well, how would we display that? We would display it with a scatter plot. If it has time order to it, then we would do a time plot. How about if we're trying to analyze somebody owning a pet and how much money they spend a week? Well, if owning a pet is the x variable, categorical, and also how much they spend a week is quantitative, we could do it with side-by-side box plots or stacked histograms. How about if we did owning a pet and do you live on or off campus? Well, owning a pet is categorical, and do you live on or off campus is categorical, so mosaic plots, contingency tables, stacked bar charts, or side-by-side pie charts right there if we have two categorical variables. Knowing what ways to display data and what the variable types are very important. So once again, pause the video here and try to write this down to remember and use this as we go through the lectures. Here's some of the ways to display data in JUMP. Now at this point, you'll be displaying categorical variables. They have the little red marker right here next to them, but sometimes there's a count of how many individuals there are, which needs to be put into the frequency. This is a bar chart. Notice how below it, we see the names of the categories, and then we get the frequency for the count and the relative frequency for the probabilities. There's the relative frequency and frequency of the observations for the data. We have other ways of doing this with the tabulate function right here. So review the slides if you want to see how to make some of these. You'll also see me do some of these in class. Now, pie charts can be displayed pretty crazy, and this is not good because if you notice the 50% right here, not so much looking like 50%. Also, use alcohol and heavy drinking. Well, that's kind of overlapping in the categories right there. So I don't think this is a really good pie chart right here. It doesn't display the data well. Last but not least, Pareto charts, I like to say, put them in order. So you should have a note right now. What's a Pareto chart? It's a bar chart that's been put in order. Now this one has some extra little accoutrements on it. You'll notice that we have a frequency over here, which actually has a continuous amount. It's still categorical data, but they did it as a continuous frequency. Still, once again, categorical data collected. And over here, we have the relative frequency. So they put two scales, two axes on it. Then the line right here is a cumulative amount across. If you were to add these bars on top of each other, you're stacking up the bars, these bars below to see the percent or the total amount. This is not required. The only thing that is required to make this into a Pareto plot is to what? Put the bars in order. All of this extra stuff right here is just extra, which is fine. But if the bars have been put in order from most to least common, it is a Pareto plot. There's the Pareto plot with a frequency axis. That's all that's required to make a Pareto plot. Once again, Pareto plots are for univariate, one variable you've collected. Why were you late to work? That's what we ask people. What was the reason? And then we collect from individuals. They say, oh, it was traffic. That's why I was late to work. Categorical, univariate, one question asked, Pareto plots, the bar chart put in order. So now let's get into displaying quantitative variables. Quantitative variables are actual real numbers, which means when I tell you 5, I'm not saying, which group are you in this class? I'm in group 5. That's not how much my group is. That would not be quantitative. If I say 5, you say, well, how much money do you have in your pocket? Well, $5. That's a quantity of money in my pocket, so it has to be actual real numbers. So think of a question yourself here that would be quantitative, and how could we display that? Let's go to exam 1 scores. Exam 1 scores are quantitative because we could do something like display it in a histogram and it's actual real numbers. So here we are. Exam 1 scores are usually skewed to the left. And we might see something like this right here with a little bit of left skew, and they could be centered around like 75. A stem and leaf plot is where we see the actual numbers. So we might put here a 7, an 8, a 9, and a 10. And this is the stem. And then the leaves here would be like someone made an 82, an 81, a 78, a 91, and a 100. And then we have a key down below where we say this equals 100. We're going to go more in depth on these, but I'm trying to draw little tiny figures of them, which you should also be able to draw if someone said, what does a stem and leaf plot look like? You say, well, it has a stem, which is the number line, and it has leaves, which show you the actual observations. I want to point to something. Notice how this is a number line, and the histogram also has a number line. Then the observations are this part of the histogram, and the observations are this part of the stem and leaf, where you see the actual data points, and you can actually see the values. One of the pros to a stem and leaf. The dot plot is also going to have a number line, like the 70s, the 80s, the 90s, and then we simply put dots to where the observations are. Wherever the numbers are, we put dots, and you can kind of tell the frequency of observations, sometimes a little bit better with a dot plot. And so once again, we have the data right here, and the number line, which just represents where they are in distribution to each other, down there on the bottom. So all of these are just different choices if you wanted to display scores on a test. So a histogram is a univariate. We're asking one question. What was the score on test 1? Display of quantitative data that lets us look at how things are distributed. Distributions and the way things are distributed just means the way they're spread out. Are they tightly clustered together? Are they distributed really closely? Or are they distributed far apart? So when we look at this right here, we can give an understanding about the distribution of ages on the Titanic. There's a slight little mode down there, not a strong one, and a huge mode right there. So you've kind of got like babies and stuff like that on the Titanic, and then you've got young adults. And that's where we see most of the data. It's just that there's a little bit of an unusual peak right there. There's not a lot of 10-year-olds, but then you get to like the 1- and 2-year-olds. It's kind of interesting about the Titanic that there's a lot of like little babies, and like, hey, want to take your baby on the Titanic? Let's do it. So with this right here, there's a very much smaller second kind of area that I find of interest. And then we also see a sharp peak around people in their early 20s, which declines towards the 30s, 40s, 60s, and beyond. What ways of describing this data more in depth? Is this really a second mode? It's much weaker. That one's the main mode of the data. To display data like this in JUMP, we will do analyze distribution, and notice now that the variable is blue. Blue means quantitative. Analyze distribution and insert a blue variable, and you will get a histogram right here. The red arrows you'll notice right here are how you add extra things in JUMPs, like you can stack it to put it in horizontal layouts, so it usually comes in vertical layout. Stacking it puts it in horizontal layout, and then you can add a count axis, you can change the color of the histogram. Lots of fun things you can do, not all required unless we ask you to do it on an assignment. You can change the bin widths on a histogram. The bins are what collect the data. This is the exact same data right here, and it looks different because the bin widths are smaller down here and they're larger up here. You can actually make it just one bin, and that's a bit ridiculous. So watch out. Usually JUMP will do a default bin width, how much data is collected within there. And notice how more data is collected in the larger bin width, making a higher counter frequency, and there's less data down here. This doesn't change your data, it just changes the way it looks, and JUMP's default is usually what you go with, so not too much to say about bin width, other than it's how wide are the bins. Bin width right here is pretty easy to calculate, because you would just ask how long are these. The bin width is not 1, the bin width right here would be 0.5, because this would go to 6 6.5 right there because there are 2 bins between 6 and 7. So it goes 6, 6.5, 7, 7.5. It's how wide are the bins of the histogram. The bin width on the bottom looks to be 1, 2, 3, 4, 5. I think that's 5. Let me double check. 1, 2, 3, 4, 5. Yep. So the next bin over would be 6.2, and the bin width would be from 6.0 to 6.2. So a bin width of 0.2. It's just literally how wide is that thing on the number line. That is the bin width. We can change bin width in software, like I said, but usually JMP does the default. To figure out bin width, simply ask how long is the number line and how many bins are between it. There are 2 bins between this, and the number line distance is 5, making this bin width 2.5. The bottom one is tougher to calculate because there's not really good portions on it, except to say, and you can see it right here, this goes to 57.5, that's where that would be. And then over here, it hits right here at 72.5. I would not like this as a test question. And so that's a distance of 15. You just ask how long is that distance. And then there are 1, 2, 3, 4. So this is a bin width of 3.75. And you'd kind of check your numbers right there. I think that's correct mathematics. Not the best of bin widths, but once again, this is the same data, and it can look different when you change bin widths. If we ever put a test question, I'd prefer something much more like that, where you just look and you can see clearly that it's this would be 67.5, and thus the bin width right here is going to be 2.5. Bin width is not the number line length. That's where usually people get it wrong. It's going to be the width of these literal bins right here. How wide are those bins? Careful, it's not the number line. A stem and leaf is going to show you the observations in your data. So what do we mean by that? Where a histogram just shows you the shape of it, the stem and leaf is going to show you the actual observations. What I like to show people is if you take this data right here, turn it on its side, and watch this, we'll turn up the opacity on it with the picture format. I think a lot of people realize this. We'll go to transparency, make it more transparent, and then we'll overlay this on the histogram. And my guess is that we could make this in such a way that it overlaps nearly perfectly. Look. There we go. Look at how now the number line, we'll raise this up right here. The number line down below with the 50s, the 60s, the 70s, the 80s, and the observations, you can actually now see that there's someone who has a heart rate of 80, 80, 80, 80, 84, 84, because there's 6 women in this bin. This person was the highest heart rate of 88. So when you think of a stem and leaf, it is a histogram where you can see the observations. You can even draw your histogram over it right here and look at how it has the same shape because it does have the same bin widths. So we're very close. No, it does have the same bin widths. Good. 80 to 85, that is a bin width of 5 right there, just like the lower 60s right here and the upper 60s right here. So with this, a stem and leaf is just going to be basically a histogram where you can see the observations. When you want to know how many observations there are, you would simply count up how many numbers there are over here on the right, just like you could count right here like 1, 4, 4, 4, and we're just counting over here, 6, and 1 to see how many there are, and we should get 24 women if we add up how many observations there are in these bins. Make a stem and leaf right here. First make a histogram, and then click the red arrow where the options are at, and then go to stem and leaf. And once again, stem and leaves need keys to tell you that 50-6 represents 56, and the count is there's 1 individual in that bin right there. Now you can do back-to-back stem and leaves. A back-to-back stem and leaf is no longer a univariate display of data. Think about this. What you would do to collect the data, you would have to ask, what class are you in, and what was your grade? By doing that, you've asked 2 questions, and now you're displaying it. So this is actually a categorical variable right here, and then what is your grade is quantitative. So a back-to-back stem and leaf is a bivariate display of data that has a quantitative y of interest and a categorical x. So right here, you can see all the quantitative responses. Someone in class, Professor A, made a 100, and we would need to fill this out right here. There's the 92, so here's the 94. We could go through and fill out this full thing right here. See if you can do it, or see if you can add things to it. Let's go to Professor B. The lowest grade was a 39. Where would that go? Well, it has to be under Professor B, and there's the 39. And you'd read it 30-9 represents 39. It is weird that when you're on the other side, if you want to input the 74, you have to go 4 right here. And remember, each of these represents a different observation. So you sometimes even see stem and leaves with commas between, so people know that each observation is different. It's not just a string of numbers right there. Not all stem and leaves use numbers, though, as we just saw in this jump example right here. Each of these is an observation, hence there's 6 observation, meaning that the first woman had a heart rate of 80, 80, 80, 80, 84, 84. Going to this data right here, someone had a 92 in Professor A. Somebody had a 94 in Professor A. The stem and leaf is going to be a visualization of quantitative data, and if it's put back to back, we've added a second variable to add a categorical variable. We next have dot plots, and I like saying dot plots because dot plots are just histograms where they're dots. Not much else to say on that, but dot plots, this is a bimodal distribution. Dot plots are going to be histograms where we just have dots. Univariate display of quantitative data. Now we get into a big thing. Shape, center, spread. Well, when we do this, we must know first the shape, which then will dictate the center and the spread. Let's draw something out right here. Shape is going to be one of two shapes, really. Let's put here shape. And shape is either going to be normal or skewed. Normal or skewed. I'll tell you what those mean in a moment. Now, when we do center, if it's normal, we'll do the mean. And if it's not normal, we'll do the median, which can be skewed. When we do spread, spread will either be, for normal, the standard deviation, and if it's skewed, the IQR. So take a look at this right here. This is very important because the first thing you'll need to decide on is the shape. As soon as you say normal, you've just decided, if you do say normal, the center and spread that is appropriate for this data, mean and standard deviation. If you say skewed, you just decided that the center is most appropriately the median and the spread is the IQR. So the first decision, and really the only one in talking about center and spread, is how is the data shaped? And let's take a look at what shape can look like more in depth than normal and skewed. Well, the first thing we have right here is the central humps of a distribution, or the modality. Let's talk about that. Modality means most common. So when we talk about modes, it can be unimodal. One mode. This is the uni mode right here. Bimodal, 2 modes. Bimodal, 2 modes. Multimodal, multiple modes. And bimodal is technically multimodal. So bimodality is 2 peaks to the data. I like to ask students, how many mountains are in this mountain range? And that looks like 1 mountain. But at some point, we might get 2 mountains, and that would be a bimodal data set. And this is a little bit subjective, so sometimes people might say there's a weaker second mode, which I did earlier on. So once again, we want to give a general understanding, but this right here is a clear example of unimodal, second one's a clear example of bimodal, and the last one is a clear example of multimodal data. There's one other way data can generally be shown without modes, and that would be uniform. What does uniform mean? It means it has one form, uniform. Uniform data is generally flat. Now, this is not perfectly flat because it would be perfectly uniform then. This is generally uniform. Uniform data is flat and doesn't have any strong peaks. If you were to go out here to this mountain range, and this is you, well, if you were to climb up it, really the first climb would just be up here, and then you're just kind of walking over a nice level ground. So this doesn't really have any strong modality or strong areas of concentration. It's kind of evenly-ish spread out across. Things like dice rolls 1 through 6 are a good example of uniform data. Now, symmetry is either symmetric right here, where if we take it and fold it over onto itself, it would generally look pretty even. It doesn't have to be perfect, but we can say this is pretty symmetric. Notice how we use a lot of qualifier words. We don't like to say things are perfect in statistics. We'd be like, it's got some slight bimodality, it's pretty symmetric, it's mostly symmetric, but not everything is symmetric. Here is something that is not symmetric. You can't fold this over on itself, so it's not symmetric. And things don't have to be unimodal to be symmetric. It can also be bimodal and symmetric. Notice how you can fold this over on itself and it would be symmetric. It would look the same when you do that. And things that are not symmetric are often said to be skewed. Now, this is where we get to the monster man. Everyone knows this from my classes. We have a saying, right to the high, left to the low, whatever way the monster man's tail goes. Right to the high, and what do we mean by that? This is the high side of the data. And then left to the low, this is the low side of the data, whatever way the monster man's tail goes. Right to the high, left to the low, whatever way the monster man's tail goes. So when you think about this right here, is the data skewed to the left? Is it skewed to the right? Draw your monster man to find out. Now, one important mistake people sometimes make is that they don't put the number line from lowest to highest. Be careful, if you have data, it should look from lowest to highest, and this is the way the data has been oriented here, from the low side to the high side in that order. And if you draw it this way and you look for the monster man's tail, you can figure it out. There are statistical ways to figure out skewness, and this can also be called negative skew, and this can be called positive skew, and something that is symmetric has zero skew. We can mathematically derive the skewness, but a lot of times if something is skewed, you can usually look at it visually and also mention if it's left, negative skew, or right, positive skew. So how about things that are unusual, outliers? Outliers are things that are far away from the rest of the data, and they're usually accompanied by gaps in the data. I ask this question a lot of times, and it tricks people. I say, how many outliers are there? And they say, 1. Not quite, because you have to look at the frequency of the data. 1, 2, 3, 4. There's actually 3 observations in that bin right there. So there are 3 outliers in this data set regarding people per housing unit and the amount of cities that have it. So this right here is 3 outliers, and notice the gap right here. We've got a gap in the data where no data exists, and this is something unusual in the data right here. And this is everything we've been dealing with talking about shape of the data. So remember, in review, the things you should have written down for shape are going to be the modality of the data. Modality of the data is going to be how many modes or areas of concentration are there. Next, we have also, it doesn't have to have modality. It could be uniform, which is no area of concentration, flat. Next, we have symmetry. Does it fold over on top of itself? Then it's symmetric. If it doesn't, it might be skewed to the left, skewed to the right, right to the high, left to the low, whatever way the monster man's tail goes. Outliers and gaps are things that are unusual, and usually we see outliers with a gap between them and the rest of the data, like we see in this example here. And that gets us to understanding how we can interpret center. Now remember, you only pick center based on if it is more normal looking, and by normal, we mean unimodal symmetric. So it's unimodal symmetric, one mode, and it's symmetric. That's going to be your normal shape right here. So the normal shape, the more normal it is, the more we use the mean. And the more skewed or unusual it is, the more we use the median. So someone could ask, well, wait a minute, what about some data that looks bimodal with no skew? You're probably fine to use the mean due to lack of skewness. Is it really that unusual? How about uniform distribution? Well, that doesn't have high skew. You could probably use the mean right there. But the number one time to use the mean is when data is normal. The number one time to use the median is when data is skewed. So you've got this shape right here, and then if it's skewed, use the median. So median is going to be the center for skewed data, and then mean is going to be the center for normal data. How does the median look? What is the median? The median is the middle number, as in, if you had people standing in a line and they were 18, 21, and 20 years old, what would be the median age? There's a little bit of a trick question right here. Because you might say 21 immediately. But when you do the median, you have to put the numbers in order before finding the median. And putting the numbers in order, the middle age is 20. What about if another person joins in and they are, let's say, 19 years old? Well, now putting the numbers in order leads to there being no middle number. 18, 19, 20, and 21. What we do now is we average the two middle numbers. So you would get right here the median, which is a number that doesn't exist, is 19.5 for this data set. We'll show the way to do these mathematics on the next few slides, but we also want to know that the median represents the 50th percentile. Half the people would have an age at or above the median, and half the people would have an age at or below the median. So if we're talking about the data set over here on the right, we would say 50% of people in this data set have an age at or above 30, and that's what the median represents. Always make sure to interpret your data in context when talking about data. So here we are with another data set with a small amount of numbers, and you can use this formula right here to figure out the position of the median. Be very careful, this is not the median. Step one, put your numbers in order. So take the numbers you're given, put them in order, and then find out the position of the median. If you have 7 numbers right here, take 7 plus 1, divide by 2, and the median is the 4th number right here. If you have an even amount of numbers, an even amount of numbers will lead to a median that is a position that is an average of 2 numbers. So notice right here, we can once again do the same math where we find out the position of the median. And if we go right here and we do a sample size of 6, 6 plus 1 divided by 2 equals to 3.5. The 3.5th position is between 3 and 4. And once again, we would average these numbers to get 5. This formula right here, I'll highlight it in yellow, gets you the position of the median when numbers are put in order, n plus 1 divided by 2. I prefer just to write out my numbers and see where the middle number is. Just put them all on a number line right here and find out if there's no middle number, average them together. And if there is a middle number, then it is the middle number. So just like in the smaller example, if you had the numbers put in order of 2, 5, and then 8, the middle number right here would be 5, and 5 is the median for that very small data set of 3 numbers. Put the numbers in order, find the middle number. If no middle number exists, average together the 2 numbers that are at the center of the distribution. When do we use median again? Number one thing to know using the median is skewed data. Right to the high, left to the low, whatever way the monster man's tail goes, this is right skewed data. And by the high side, we mean the higher numbers, also known as positive skew. The median will also be found over here where the IQR is at in jump. So you can see the median of this data set is 1.9. 1.9, it would represent the 50th percentile of wind speeds, as in 50% of wind speeds were at or above 1.9 and 50% of wind speeds were at or below 1.9. The mean, which will be used for unimodal symmetric data, and you can use it for mostly symmetric data, I prefer to use it more for normal data, is going to be the average of the observations. So the average individual. Be careful, median is not average. Median is 50th percentile. Mean is average. An interesting thing about the normal curve, is that the mean and median are in the same spot, and also it's where the mode is. That's where the peak of the data is, that's where the 50th percentile of the data is, and that's where the average of the data is. So the peak is right there, all those same things are in the same spot. How do we get the mean? A lot of notation on this screen, and we should know what it all means. Well, to get the mean, you would have observations which are y's. So what is an observation? Well, if you ask someone their age and they say, I am 18, that's an observation. Someone else says 20 and someone else says 22. So these are the y's. Those are the observations. Now we take a sum of the observations, which you would just add them up. That's summing the observations, and we would get 60. And then next, we find out the sample size, which is how many observations were collected, which is going to be 3. And this will give us y bar, which is the sample mean. So y bar in this instance, the sample mean of this data set is 20. 60 divided by 3 is 20. And think about this. The bar up top is the important part right here. If you notice the bar The bar is when we're talking about the mean of variable y. Sometimes you'll see x bar, and that's the mean of variable x. So when you hear y bar, it means sample mean of variable y. Let's write that out right here, and this is something to understand. Sample mean of variable y. And to understand why this is so important is later on you might hear things like mu or mu sub y, and that'd be the true mean of the y variable. You might hear things like x bar, and that would be sample mean of variable x. Or you might hear mu sub x, the true population mean of variable x. And I know I said true population this time because you can go more in depth on your answers of what things are, but the notation here is going to be very important. And the important thing to know about this is the bar. The bar used in statistics over a letter usually means mean of that, and that's just the variable we collected. We called this a y variable. We just said this is the thing we're interested in, the y variable of interest, and now we've taken the mean of those data points collected as a variable y. The truth for all the data, which we probably don't know, would be mu sub y right there, which would be the population mean of variable y. This notation is going to be very important right here. We're just making sure on this slide you know that when you see a bar, it means mean of that variable, and sample mean more specifically. A lot of times data sets are very large, and we're not going to find this out by hand, but the mean is sort of a balancing point. Once again, you're averaging everything together, so it would all kind of average into this, and that's how we get the mean right there. It's not the 50th percentile, and when data is skewed in this instance, the mean follows the skew. So if you notice right here, the median is at 1.9, and then the mean is going to follow the skew, and there's the mean right there at 2.13, and that's actually where the mean is at, that little dime in the center of it. And so since this is right skew, the mean is to the right of the median. So data that is right skewed, an important note to have right here, data that is right skewed will have a larger mean than median. Draw your monster man. He's skewed to the right there. Looking at his tail back there. So right skewed data has a higher mean than median, but left skewed data would have a lower mean than median. Because now the mean is going to go in this direction. It goes in the direction of the skew. So right to the high, left to low, whatever way the monster man's tail goes, so does the mean. Now be careful because there can be drastic differences. You first look at the shape of the data, and if you had data that looked like this, notice how your mean is being inflated due to the outliers, which also show a gap in the data, from the unimodal, extremely right skew data, extremely right skew, and the median is lower than the mean. There's where the median is at with that blue line right there. The mean is pulled to the right for this data right here. And look at all the concepts we have that we've been talking about. A unimodal, extremely right skewed data set with some very moderate outliers. And so these are moderate outliers, put an M outlier over here, and we have extreme outlier over there, at least one extreme outlier. Understanding, talking about the shape, is going to first help us determine what proper center we should use. And beyond center, we're also going to talk about the spread of the data. So the spread of the data just means, how is it spread out? I like to tell people, how do you like to spread your butter on your toast? Some people might go here and just have a blob of butter in the center. Hey, you do you. Some people might take their butter and spread it out more uniformly across the data set. Notice how we're bringing back this. Maybe someone said, I prefer a normal distribution of my butter. They take their butter and they do a light sort of amount around here, and they do like concentric circles and do like a big blob at the center, just a big normal mountain of butter in their thing. It might be good. I don't know. I haven't tried it yet. So how do we have this distributed and think you can spread it out and distribute it more evenly across? But that's when we're talking about spread, is how are things distributed across a number line. And it looks like this when we talk about data. You could have two data sets of scores on a test, where in the data set up here, scores are more spread out across, or they're more concentrated in one spot. So you can see they're tighter, less spread to the data in the distribution I draw the second time, versus the top one has more of a spread to the data. So when we do this, The number one thing to determine again here is the shape of the data. We will also know our center from this, and then the appropriate spread. One metric we can always use is the range of the data. And the range of the data is the max minus the min. When you think about range of data, simply ask yourself, what was the lowest score on the test? 20. What was the highest score on the test? 80. And then think about their distance. Now, technically, you need to do 100 minus 80, or excuse me, 100 minus 20, and that's going to lead to a range of 80, which is the distance between the lowest and the highest score. The problem is this only incorporates 2 data points in making this decision. So maybe this person right here who made the 20 is extremely far away from the rest of the data. If we look at the shape of our data, we might see something like this, where they made the 20, and the rest of the data is over here, and thus the spread measured by range is not going to be representative of what's going on in the overall data. There was just one extreme outlier. So an important note to have right here, outliers can drastically impact the range. Think about an outlier, it's usually going to be on the extremes, and that's where outliers are, and thus they would be the max or the min, and with that in mind, they're going to drastically impact the range. So we're not usually a big fan of range, even though you can always report it. You might want to mention if it's due to outliers. What we are more of a fan of is the IQR. Now, IQR sounds very complicated, but it is the interquartile range. And what would you need for the interquartiles? Well, first, let's go ahead and try to understand what the quartiles are. We have right here Q1 and Q3. Q1 is when you've gone through 25% of your data, like Q1, 25%, 1/4. Q3 is when you've gone through 75% of your data, there. Let's draw some visuals to help get a better understanding of what these percentiles mean, which you can see the percentile right here, as in the 25th percentile and the 75th percentile, to better understand. If you have data, we'll erase this for a moment, and your data looks like the following. You have a student who made, let's say, a 30, a 40, we'll go to some better grades, a 55, a 66, a 78, an 80, 90, and a 92. Now, with this in mind right here, we would want to understand the IQR. So what is the IQR? It's the range of the middle 50%. And let's think about what 50% of this data would be. Well, if you have 8 observations, you would then have 4 observations in the middle. So the middle 50% of this data is this. Here's the outer 50%. The outer 50% is this, the lower 25 and the upper 25. So think about why we call it Q1 and Q3. Because at this point, you've gone through 25% of your data. At this point, you've gone through 75% of your data. And the range of these numbers right here is going to be the IQR. Now, I gave myself a pretty interesting one right here because there's no number exactly where Q1 is, which means Q1 with this data set right here, we don't usually do these by hand, we use calculators or software, Q1 is going to be 47.5, and Q3, which is going to be the average of those other 2 numbers, is 85. To find these values, I'm using the same idea as we used for the median, where I'm averaging the values of 40 and 55 to get 47.5. I'm doing the same thing up here between 80 and 90, averaging them to get 85, which is the Q3. There are other values to talk about too, though, such as like Q0, which is going to be when you've gone through none of the data. You could go here, which is the min, and then Q2, and then Q4. So other names for these data points right here could be, instead of Q0, we could just call this the min, the lowest value in the data set. We could call Q1, Q1, and we could call Q2 the median, because that's the 50th percentile. Q3 is going to be Q3 right there, and then we could call this the max. And what we actually have listed out right here is the 5-number summary. One thing I also like to point out is you can draw 4 quarters. If you draw 4 quarters, you can see as you go through your data set, Q1 is after 25% of your data. The middle Q1 to Q3 is 50% of your data. And then Q3 to the max is another 25% of your data. And what do we mean by this? This represents 25% of the data here. This is 25% here, 25% here, and 25% here. Try doing your own drawings of these, taking these notes, pause the video. Once again, the more notes you take as you go through your notebook is going to help you remember these things. And if you put it in your own words, that's even better. So Q1 to Q3 is the range of the middle 50% of the data. We'd simply go right here and subtract those numbers and get 37.5. So Q3 minus Q1 for the data set I did equals to 85 minus 47.5. You also don't have to worry about which way you subtract it because we talk about it as a positive number. So as long as you get the numbers, you can just make it positive, preferably do Q3 minus Q1. And it's kind of like max minus min. I always want to point this out to people because if you look at this data, the range is big number minus small number. That's the range of the data. This data has a range of 62. And then the IQR is the range of the middle 50%, interquartile range. Here's your interquartiles, and their range is the big number minus the small number. And hopefully that's like an aha moment for people who are like, oh, the interquartile range is the range of the middle 50%, the interquarters. So the two middle ones right there, the middle 50% of the data, it's range, and that helps you interpret and understand what you're doing. Here's what it looks like visually. A range of the middle 50% of the data, once again, would be Q3 minus Q1. So you can see Q3 minus Q1. Also, if you think about that, if you have 3/4, you subtract 1, that's 2/4, 50% right there, helping to memorize the formula of Q3 minus Q1, if you have to memorize it. Finding the IQR right here, usually we put this into software. You can find the medians of the data sets right here. If you look at this, this would be the median between these numbers is 49, and we have 22 numbers, so we'd go right here, and that's 11 numbers, so you do 5 right here, and 5 right here, creating your little balancing beam, and there's that. And this is nice and neat, which would be 13, because you've divided it into a higher set and a lower set. I will say this, I'm not a big fan of finding this by hand because there are many ways to find this. You should probably use a calculator, and I'll put some videos in the links or suggest them to go and do this with a TI calculator or use software like Jump. So in our class, we'll use Jump right here, which you can see Jump finding you the data, and they do have different ways of finding it. So you have to watch out because the finding it by hand way can be different than the way the software does it. It's just that different statisticians come up with different ideas on how to solve these questions because it's not always exact. So I would highly suggest if you're doing it by hand, you might come to a different conclusion versus Jump, which is going to show you this right here, which is slightly different. We would need to do 55.25 minus 41.75. That's a 7 right there. I think last I checked, there are, I think, 9 different ways to figure this out. So statisticians don't agree on it. And to find the IQR on this output, you simply take Q3, which is the 75th percentile, minus Q1. Don't subtract the percentiles right there. Take the numbers and find their difference. So try answering this for yourself, but the IQR is going to be 126.25 minus 39.5, and that is going to be the range of the middle 50% of the data. Once again, think about it as a range, as though you're doing max minus min, but only for the middle 50%. Why do we use this? It excludes outliers. So once again, this is for skewed data. It's not going to be impacted by outliers. But what if we have normal data or data that's mostly symmetric? Well, then we are going to use the standard deviation. And the normal curve generally goes out 3 standard deviations. 3 standard deviations. So if you were to put standard deviations below this, you would see +3 and -3 standard deviations. Right now, we're just looking at a deviation from the data. What do we mean by a deviation? A deviation is how far away is an observation from the mean. That's just a deviation. We haven't done a standard way of talking about the deviation. To standardize the deviation, we now do it based on squared units. You might wonder, why are we doing the sum of the squared differences? This is the differences from the observation and the mean. Remember, y is an observation, like a singular point, like your height. If you are 75 inches tall, you might be 7 inches taller than the mean. So that is going to be a difference of 7 from the mean of that data set. We then square it, which would be 49, and then we sum it with all the other observations, like someone was 2 inches shorter. Well, that's -2 squared is 4. Notice that the squaring of it makes it positive so that all the numbers can be added together without them going towards 0, because if you don't square them, you would get 0. So we sum up the squared differences to get a quantity of how far things are away, and then we divide by n minus 1. Now this is in squared units right now before we square root it. And the way to think about this formula, if you think about what are we doing, we're figuring out how far are things away, and let's highlight that as we talk about it. How far are things away? Then we're squaring it to make it all positive. Then we're kind of averaging it. That's almost an average. It's an n minus 1, which is what we use for the sample. If we did the population, then the population would not use the n minus 1 because this is a sample standard deviation. So small difference in formulas, if we were to do sigma over here, sigma would use that. Small differences. And with this right here, that's kind of averaging it. And then why do we square root it? To bring it back to units of the problem. So a standard deviation is a typical distance things are away from the mean. That is the best definition I can give you on what a standard deviation is. It's a typical distance observations are away from the mean. If there's outliers, it'll greatly inflate standard deviation because outliers are a lot further away from the mean. And that's why we don't use standard deviation when there's outliers, because they inflate the standard deviation. And it's also calculated from the mean, so this is derived from the mean, and we don't use outliers generally. We don't use the mean when we have outliers. Now, one thing we can do, and I'm not a huge fan of this, is we don't have to square root it, but we would then get standard deviation squared, which is the term variance. Variance is in squared units, so I'm not such a big fan of it because in squared units, a lot of formulas will use variance. If I'm talking to people in context of data and I want to know how far things are typically away, I'll talk in terms of standard deviation. So typically, and if this was more normal data, it would make more sense to say, wind speeds vary from the mean by about 1.3, but this is probably heavily influenced by outliers, inflating the standard deviation right there. Going down here, we can think about when would standard deviation be larger. So which of these would have the largest standard deviation? Well, the one that has the largest typical distance from the mean. Here's a hint. They all have the same mean. So which of these do you think has the largest typical distance from the mean? The answer would be B, because it's more spread out away from the mean. The uniform data set probably has the second largest, and then this one is more centralized. This is going to be the smallest. This is going to be the largest, and then the uniform is between it. How about other ones? Looking at the top data set right here, which one has the largest standard deviation? Which one has the most spread from the mean? Go ahead and mark where the mean is generally at, the average. So the average is there. And it looks to me like this one is more spread out from the mean. How about these? Well, they have the exact same shape. So same standard deviation. With this right here, which one's more spread out? Here's the mean of this data set. Here's the mean of this data set. Number line's the same, so this one is going to be larger right here. This one looks more spread out down below. It is hard to tell. Technically, it might be this one, probably because there's gaps creating more of a spread. That is a tough one. I'd love to see the data and know for certain. By my estimates, it's going to be A, but that is a very close call, not an easy one. Top graphics here is very easy because the mean for both of these is towards the center. They are both symmetric. The second one's unimodal, the B graphic. And you can see this is more spread out, so it is larger, versus the one that's clumped up would have a smaller standard deviation. Right here, you see a clump at the center, leading to smaller standard deviation because it's tight around that area. But this one has a little bit of right skew, which is going to increase the standard deviation. Skew and outliers increases standard deviation. In this one, you see the same graphic here, but it's been more spread out. More spread out means larger standard deviation. This graphic right here is a mirror image. So if you just invert a graphic, it doesn't change the way it's spread out or distributed. So standard deviation is going to be the same. This one right here has two peaks, and they're across the same amount on the number line. And it looks like this one's more centralized. So this one, which is more spread out on the sides, think about it, you're pushing it out towards the side, it's more spread out away from the mean. That one would be a larger standard deviation. Now the last one is a trick, because in the last one you'll notice this one looks more spread out. But the number line here indicates a much larger spread. Now, it might be hard to tell, especially if you haven't done a lot of statistics, but you can sometimes take the number line and divide it by about 5 or 6. There's no exact rule for this. If I were to guesstimate and do 16 minus 3 divided by, and we'll go 5 because there's no exact rule for this, you would get 13 over 5, which is going to be 2.6. My guess here is 2.6, and this one right here goes from 0 to 6, so 6 minus 0 divided by 5, and that would lead to a 1.2. And as I suspected by my estimates, the one on the right has a larger standard deviation. Now, you're not meant to figure these out by just looking at them. It usually takes practice and understanding that data that is more spread out, very clearly the top one right here is going to have a larger standard deviation because standard deviation is a metric of spread away from the mean. But understanding and using some tricks like here, like I often have to figure out a guesstimate of it. It's not exactly 2.6, I'm sure, but that's a decent guesstimate of it. So what can we tell about variables? What's important to know? Well, the first thing is going to be the variable type. When you're doing the type of a variable, make sure to first identify. If you are doing something like policy number, that's going to be an identifier variable. Identifier variables are something we rarely ever graph. Just because there's really not much information about them, they are unique. Do not graph identifier variables. We can make tables, charts right here. We don't do shape center spread for bar charts because that's categorical data. Make sure to explain everything and talk someone through what your data means. Histograms are going to be for quantitative variables, where we talk about the shape, center spread, the modality is part of shape, the symmetry is part of shape, the unusual features, the outliers and gaps. Describe the center and spread. Once again, we're going to talk to somebody about the median being the 50th percentile, the IQR being the spread of the middle 50%, and that's if it's not symmetric, if it's more skewed data. And then also we have right here the mean and the standard deviation are going to be used for metrics of center and spread. Same goes for median and IQR, but for skewed data and symmetric data, which looks more unimodal symmetric, technically can be used for other symmetric data sets too. And that should do everything right here. Great work. Make sure to know when to use which metrics of center and spread and what graphics we use. If you have questions, let me know.